so today we'll take a look at something very, very interesting, something intellectually very, very challenging. The math is beautiful behind the derivation. So hopefully you guys will start to appreciate the direction in which the modern AI or the deep learning is progressing as we discuss today's topic, right? Okay, so two things I'll cover today. One is Siamese networks, which we started on last time. So let me at least give you the idea. Then I've already given you a handout, which has the equations that we partially developed last time. So the purpose of the Siamese networks is basically to detect whether two images or data. So it doesn't have to be images, it could be text as an example, right? Are similar or not. Okay, so a lot of the modern AI, or I should say some of the current research that's going into AI is really, as soon as we identify what our goal is, to accomplish that goal, basically what it means is we have to come up with an appropriate loss function or the error function which guides the parameters of the network in that direction so that we can accomplish that goal, right? So in this particular case, like I said, the goal is feed two images. So if this is our network, okay, so this could be a CNN network because as you guys saw, by applying multiple convolutions, we can, enhance the data, recognize some of the important features. The last part of the CNN network, if you recall, is basically a regular NN, regular neural network, right? And before we go to the regular neural network, what do we do to all the convolutions over here?
Flatten it out.
Flatten it out, right? So flatten. Okay. So anyway, and then the regular network will do the classification. Okay. So the idea in the Siamese networks is create two of these. So let's pretend we create one more CNN network. Okay, so the last part will be also some kind of a flattening going on. Okay, and then what we can do is, because now the goal is to make it similar or dissimilar, so we're not trying to, for example, recognize whether it's digit 5 or digit 2. So we remove the output network. Okay. So after flattening, we could feed it to just a single layer network. So let's say we feed it over here. So there might be, for example, we may decide, e.g., 100 neurons. Okay, so this is what will be the output produced, 100 outputs over here. Okay, so same thing, the second one also, the flattening will go into, again, let's say this is 100 neurons, this is 100 neurons, right? So basically then we compare these. Okay, and suppose we call it some kind of a distance. Okay. Suppose we call this A1 of A1, A2, so this is the output A1, the actual output A1, actual output A2. Then DW, for example, will be the distance, like a Euclidean distance between the two, right? Okay, so for example, the goal will be if we feed into to the first network, we feed in, let's say, 5 to the second network. Okay. Then it should tell us that, so pretend over here, we further say similar or dissimilar. Okay, so by taking a look at the distance, for example, we can say we can put a threshold on it as an example. So for example, if it is less than 50, it's similar. If it's greater than 50, it's not similar, right? So the answer will be 0 or 1, 0 for similar, and 1 for dissimilar. Okay, so coming back over here, as you can see, if we feed in 2 and 5, what will be the expected output? 1. If we feed 2 and another type of 2? 0. Okay, so it will be 0, right? Okay, so the question is, how do we build such a network? How will we train it so that we can create several pairs of training data, right? 2 with 2, 2 with 3, 2 with another 2, 5 with 5, 5 with 7. So we can come up literally lots of pairs of data so that we can train it for similar cases and dissimilar cases, right? In all of these, like I said, what it boils down to is how will our loss function work? So if we go further over here, so if I put a loss over here, and this is L, okay? So if we can define some kind of a loss function, this will be our expected output. Okay, so then if we can find the derivative of the loss function, then once we come over here, then we can backpropagate the gradients and it will work, right? Okay, so 2006 timeframe, Jan LeCun, who's one of the very famous persons who developed the CNN as we discussed, him and his students came up with the loss function for Siamese networks, right? So their loss function, we discussed this last time, was something half 1 minus y dw squared plus half max of 0, so there's a y over here, max of 0 and, sorry, max of m and, what was it, dw squared, something like this. Let me double check. If you take a look at the handout, what was the exact loss function? M minus dw, sorry. So this was 0 m minus dw squared. So anyway, so they came up with this loss function. So if we can compute the derivative of this with respect to the weights, then further backpropagate it. So the question is, how do we actually do that? How do we build it? So the handout I gave you has the detail for it. But first, to understand this, it's actually pretty intuitive over here. So this is one of the easiest loss functions to understand, in my opinion. The one I will show you for the variational autoencoders is extremely involved. Okay, but this one is piece of cake. So M over here is what we call the margin. Okay, so maximum of 0 in the margin. So margin could be, for example, 2. So all we are saying is, okay, this part takes care of the similar cases, and this part takes care of the dissimilar cases. Okay, so as we discussed, for similar cases, what's the expected output? 0. 0. So as you can see, this loss will become dw squared, right? So anyway, partial L over partial weights. So pretend in this network over here, we have some weights. So our goal is really to to determine what should be these weights so that we can do maximum distinction between dissimilar cases, and similar cases should be put close to each other, right? And by the way, I forgot to mention to you, even though theoretically speaking, you might say there are two separate networks, but they share the weights, okay? And what do we mean by shared weights? Essentially what we mean is the weights are exactly the same. Okay, so it's not like this has separate value for the weights, this is separate values. As we train it, we adjust them both for the similar and dissimilar cases in such a way so that it's the same set of weights is able to distinguish whether two things are similar or not. So in fact, in reality, once we build it, we actually don't have two separate networks. We feed it two images one at a time. So the first image we feed will go and produce some A1, right? So then so pretend this is not there. Second image that we feed over here, what will we call that output? A2. So once we have A1 and A2, then we can compute this is simply Euclidean distance. So dW, as you can see, will be A1. Pretend this A1 is a function of the weights. So if I say A1 of W minus A2 of W, for all if we have 100 outputs, we'll need to sum over all the 100. So we will take a square and then the square root. Okay, so the regular definition of the distance, as you can see, nothing special over here, right? So for the similar case, as you can see, partial L over partial W will come out to be partial L over partial dW, right? And dW, this dW further is a function of A1 and A2, which further are a function of the weights. So further we have to multiply it by W over W, right? So anyway, now what is this over here? For the similar case, Y will be 0, right? So this is just 1, 2.5 cancel. So what is this part over here?
1 minus 1.
dW, right? So then what is partial dW over partial W? We can further take the further derivative of these with respect to W, right? So now we did it partway through towards the end of the last lecture. So I've already given you the handout to save time. Let me go through and hopefully the rest you'll be able to follow it nicely. Then we'll come back and intuitively try to see what exactly is it doing. Because like I said, this, as we discussed variational autoencoders, and then later on generative adversarial networks, they are all tied together. They are all variations of the same theme, okay? Yes?
Question. What does the Y represent in a network?
Y is the expected output.
Okay. So is that, okay.
Yeah, so same terminology we've been following all along. A, we've been always indicating the actual output. Y, the expected output.
So 0 or 1.
Correct. Okay. In this case, it will be 0 and 1. But if we were doing, let's say, a classification of digits, it will be one hot vector, meaning if it was, let's say, the digit 2, the expected output will be
0, 0, 1, 0.
And so on, right? So the 10 values with the third output as the 1. Okay, so let me erase this and show you the handout.
Professor, in this case it is supervised learning, right? So we have like labels
Correct.
similar.
We have to tell it whether it's similar or dissimilar, correct? It's supervised.
So in case of similarity it would be 0. And so what is the need for the threshold? Because we already know the expected output.
Because see, this dW will be some number, right?
Yeah.
So let's pick a very simple example. From here, we went to, let's say, only 2 outputs. For the second one, we also went to 2 outputs. Okay? So now pretend this is x and y, like a number, like a In 2 dimensions, every number has 2 coordinates, right? So you can think of this as a point that was produced. So this is A1. Same way, due to the second image, we'll produce this point too, right? Okay, now during training, of course, we know what it should be, right? But once we actually put it in production, just by looking at dW. So dW could be 1.3, the distance between two. It could be 0.9, it could be 1.8. So how do we know whether given to unknown inputs, okay, whether they are, by looking at dW, which is basically a distance, how would you know? Is it similar or not? What conclusion will you draw? So that's what I mean. You have to have some kind of a threshold on it, okay? So, maybe for numbers you can say, oh yeah, this is 2 and 3, so we know, right? What if I gave you pictures of 2 faces over here? And they apparently look very similar. They look like the same person. So what I'm trying to say is, once again, the Siamese network will give us some kind of a distance between the 2 images that we fed. It's up to us to set that threshold to decide, is it the same person or is it 2 different people? So there's always a threshold set up at the end.
Or a percentage of similarity. It's like, that could give me percentage of similarity.
We could translate to a percentage, yes. Okay. Anyway, like I said, I'll come back to it because this has some very interesting thoughts or implications that we will discuss. So, okay, so anyway, loss function we already have. And by the way, for Siamese networks, this is not the only loss function. There are other loss functions as well that people have produced. But once again, if we can take the derivative of it, then rest of the training becomes easy. We can create the network. So in fact, in your next assignment, as soon as you have your own CNN ready, you will implement this particular loss function. I'll give you a face detection data set that you will try it on and see how well it works. Okay, okay, so let's go to okay, so before coming over here, I put the handouts that I gave you a printout also on the website. So during the lecture, I thought you can, if you're sitting a little farther back, cannot see it, you'll be able to easily follow it. So let me first go to okay, so that's one of the handouts I gave you, right? So let's see if we can easily go through the derivation quickly. So keep the picture in front. So our basically, so the 2 CNNs, CNN1, CNN2, right? Even though they're the same, but just for our understanding, pretend this is producing A1, this is producing A2, right? So then, as we feed through the loss function, as we already discussed in the board, so this is easy. I forgot to remind you of this margin. So the idea is, okay, let's say we feed in a 2 and a 3, right? So what would be the expected output in this case? 1, right? If I feed in another slightly different looking 2, expected output will be 0. So the question is, what if I feed in a picture of a cat? Okay, we know the expected output should be 1, right? But if we are doing digit comparisons, will it produce, if we go to the DW over here, will it produce a high distance or a low distance?
High distance.
Very high distance, right? So in fact, it will be so high that it will distort our training, okay? It will make it biased more towards very, very dissimilar type of cases. The weights will emphasize the dissimilarity more. So the similar cases will suffer. So the reason they came up with this loss function was, let's put a limit on. So this essentially defines a limit on dissimilarity. So if it's widely dissimilar, so if widely dissimilar, essentially what we are saying is, what will be the loss in this case? What will be the maximum of 0 in this particular value? So now pretend this is very high. Let's say this is 5.8. Pretend margin is 2. So what will be the maximum of 0 and 2 minus 5.8? 0. So if the loss is 0, will we backpropagate and adjust the weights? No. So nothing happens to the weight. So that's the idea. If somebody feeds in intentionally or unintentionally during training highly, highly dissimilar data, don't consider it. Don't backpropagate and update the weights. But on the other hand, you know, if it is cases like, let's say here's a 3, here's an 8, 3 and 8, you know, are looking similar, then the difference will be smaller. Even in the dissimilar cases, then backpropagation should be done. So that's the idea behind the margin. Okay.
YOLO has the same idea. The YOLO loss function has the same caveat.
Caveat.
The same principle. It doesn't penalize.
Yep, exactly. And you will see as we go through GANs as well, there will be a similar concept getting involved. Okay. Anyway, so once the loss function is defined, we'll take the similar case, dissimilar case, essentially will compute this, right? Now this we already discussed as an example. See if for the similar case, what will y be? 0. So if we take the derivative of this with respect to dw, what will this be? dw. So that's easy, right? Now let's go further. dw with respect to w, because both a1, a2 are functions of weights. So essentially, we put the formula and do the derivative. So
I'm sorry, why do you say y is supposed to be 0?
That's how the loss function is defined for. So it has two terms, one for similar cases, one for dissimilar cases. In the similar cases, the expected output is supposed to be 0. As you can see, if it is 0, this term disappears, and only half dw square is left.
So when we choose what's similar 0 and what dissimilar 1, it wasn't by random, it was by design. We could not have chosen similar 1, dissimilar 0.
We could have done, but then you will
have
change the switch this.
Okay.
But for this particular loss function, similar is assumed to be 0. Okay. So in fact, I'm working with a PhD student, and we're coming up with a very, very complicated loss function. But anyways, if I have time, I'll go over that. This, once again, is very simple. Okay, so now let's go focus on this term. dw over partial w. dw was defined to be this. Both a1, a2 are, right? And again, if we had 100 outputs appearing over here, you can see this summation will go to 100, right? Okay, so anyway, that's the formula for the distance. Nothing special over here. Square root is half. As we take the derivative, this will become half minus half. Then further, the derivative of this inside with respect to w, right? So the inside is square, so that becomes over there. Now, as you recognized it last time, what is this part over here? See if you move the square root at the bottom. This is the definition of the dw, right? So then this was already dw. So dw and dw will get canceled. Half in the loss function, there was a half already. So that half shows up over here. Okay, so now as we take the derivative of the inside, there's a square, so 2 will appear, 2 will get canceled with half, and this was that partial L over partial dw, so anyway. So then 2 comes over here, further the derivative of the inside one more time, so this becomes like this. So anyway, final result comes out to be, for the partial L over partial W to be, as you can see, what is this? Essentially the difference between these two vectors in the sum, right? So this is just a straight difference in sum over all values. And so now the question is, so intuitively, as soon as you see this, you can sort of see how it will work, right? The way it will work is, think of this term essentially as, see if we relate to our old design. If this is the loss, and this is our expected output, this is our actual output, right? So typically we do partial L over partial A times partial A over partial W. So this is already partial A over partial W, as you can see. So treat this as if this is partial L over partial A. Which, remember we used to call this delta. If we further multiply it with the activation function, okay. So like I said, usually in the last layer, if we have, if this is the output of the CNN, we typically will pass it through some more neurons. So for example, the flattening produces, let's say 256 outputs, let's pretend. Then we put 100 neurons over here. Okay, and let's say you put sigmoid over there as an example, to limit this between 0 and 1 as an example, right? So then what will be the delta in this last layer? The delta in the last layer will be essentially this term, multiplied further by the derivative of the activation function. So that will be the delta in your last layer. Once you have the delta in the last layer, then we can backpropagate it exactly like we discussed last week. So once we backpropagate it, if you take a look at these two, it tells us the gradient with respect to the first input, whatever we computed, and this would be the gradient with respect to the second input. And what do we have to do to both of them to adjust the weights? Take the difference of the two gradients, okay, for the similar case. So once again, what I'm trying to say is, let's say we fed in a tube, we fed in another tube, okay? We came up with 100 values over here, pretend this is our, so we pass 2, this gives us A1. We remove 2, feed the next 2. This we'll call it A2. And we will save all the outputs, whatever due to the first input, due to the second input, we'll save them in 2 separate variables. Okay, so this way as we compute the delta, so the delta would be computed by the difference between A1 and A2, further multiplied by the activation function. So then as we work backwards, okay, so what I'm trying to say is, whatever the weight update will be done by the difference of the gradients.
Professor, we would be calculating the derivative of activation for A1, then we'll be also calculating for the A2, then we will like take the difference. Is that what you're saying?
Okay, for this part, okay, see this, it has already told us that the, oh, I see, for the delta part, yes.
Yeah,
So for the delta part, it will be the difference of the two,
First, you'll store it in sum, and second also you store, then you
Correct.
take the difference.
take the difference. So if it's sigmoid, it will be A1 times 1 minus A1, A2 times 1 minus A2, and then you take the difference, and then that becomes the delta over here. Okay, so anyways, you program it, right? You yourself will see that it works. Okay, but like I said, the fundamental idea is compute the delta in the last layer according to this part. Then with respect to each input, compute the gradients and take the difference of the gradients to update the weights.
Professor, here we take the summation, okay, but for the old neural network, we don't take the summation because it is part
Okay.
for
Yeah,
multiply element by element. So.
the reason summation is needed over here is, like I said, we distance, see if I have a loss function, right? Okay, so before the loss, or let me do it this way. Two inputs are going in. We have to find the distance between these two. So distance is a scalar quantity, okay? So you're getting 100 inputs over here, 100 inputs over here. So how do we find the distance between 200 dimensional data?
The first summation is okay for me. The second one is
Why is it confusing? Because we further have
the gradient is matrix, right? Representing the weights. So we have like
let me see if we can clarify this part. Okay, see, we went from here, right? So then 2 came outside. Then further, this has to be, so in reality, this summation will come out to be, let's see, so this 2 came out. So this was already being summed over all values, right? So you can think of this as, okay, let's say we had 100 outputs, right? So this will be A1 of 1 of W plus A1 of 2 of W plus A1 of 100 W as an example, right?